Okay. So I will start by continuing the course. It's possible to close the window a little because too much noise. Okay. So I just remind briefly what we have done in the course during the previous session, and we are going to finish the part concerning expectation of discrete random variables. Okay. And with few words concerning vectors of discrete random variables, a topic that I will deal with in more details in a few sessions. So keep in mind that what we do for the moment is to work with discrete random variables. Okay? So I have defined what is a discrete random variable, but I am not sure that it is very clear for everybody, in fact. Okay? So I remind. A random variable is just a mapping for omega into R. Okay? We say that it is discrete when its range, that is the set of the possible values, is countable. Okay? So X discrete is the definition, means the range of X that is equal to the set of the possible images. This set is countable. Okay? In the prerequisite of the course, you have the definition of what is to be countable. You have two situations, in fact. You can be finite, okay? So you can take a finite number of possible values. Or you can be infinite, but not too much. Not too much in the sense that you are infinite as the integers are infinite. Okay? So, infinite, and in fact, elements may be written as elements of a sequence. It's what I mean by not too much infinite. So in order to lighten a little the notation, so it's just the definition that is the slide concerning the prerequisite. Okay? So, in order to lighten the notation with this discrete random variable, we are going to give a name to the set of the possible values. Okay? So, R of X, that is defined as this set, the set of the possible values. Okay, I give a name to these possible values. Okay, and I have called them Xi, I belonging to capital I, and since I have a countability hypothesis here, my capital I is countable, meaning that capital I is finite, or you may see it, if you want, as capital N, the set of the integer. Okay? So, for example, capital I can't be an interval of R. It's not possible because you are not countable in this situation. Okay? So, this is the general framework of being a discrete random variable. I have said that in this situation, in order to characterize the distribution of my random variable, it is sufficient to know what I have called the probability mass function. Okay? So the distribution of X may be characterized in my situation and with my notations by this, for all I belonging to capital I. Okay, so if you know this one, you will know all the distribution of capital X. We have seen together classical examples. Okay, so for example, if I have a random variable that is a Bernoulli 1, the set of the possible values has only two elements, 0 or 1. For Bernoulli, it's 0, 1, 2, 3 until n, for a Bernoulli of parameter n and p. For a Poisson, it's capital N, the set of the integer. For the geometric distribution, it's n minus 0, the integers minus 0. Okay? So you see that all the situations we have seen together are in this framework. The fact that the set of the possible images is countable, that is to be finite, or the elements may be written as the element of a sequence. That is a family indexed by the integers. Okay? So it means that when I consider later on this kind of symbol here, the sum, but it's a sum that is two possibilities, depending on my case. It can be just a finite sum, or an infinite sum, but an infinite sum that is not more complicated than a sum from n equal to 0 to plus infinity. Okay? So it's not sums over intervals that are not countable. It's just sum over countable sets that are just classical sums you deal with. Okay? So what I have tried to explain during the previous session is that I want to define the expectation, a kind of average value in this situation. Okay? So we have seen the definition together. Okay? So the definition I have given for the expectation is this one. It's the sum, okay, of all the possible values of capital X multiplied by the probability that capital X is equal to this value. Okay? And it's a sum over capital I. So here I repeat, you have a finite sum or a sum that will be indexed by a subset of the integers in general. Okay? My idea was to make this notation correct. Okay? What is the meaning of make this notation correct? The fact is, in fact, here, when the sum is finite, so if you have a random variable that just take a finite number of possible values, no problem, you have a finite sum. Okay, so the finite sum is always defined. But among the discrete random variables, you have random variables that take an infinite number of possible values. So it means that you have an infinite sum to compute, but first, before to compute an infinite sum, okay, I have to be sure that it exists. Okay, I want to obtain a number as the expectation. Okay, so that's why I have introduced this kind of spaces. Okay, so I remind you that I have defined L0, that is the set of all the random variables. Okay, all discrete random variables. Because we have seen together that in my definition, when I take p equal to 0, in fact, the fact that the sum is finite is always fulfilled. Always. Because the sum of all these quantities is equal to 1. Okay? So if you take the definition of LP here, taking p equal to 0, you have the sum of the probability. The sum of the probability is 1, so it is always finite, meaning that all the discrete random variables belong to this space here. Okay? So why I need a little bit more? But I need a little bit more because I want to make sense to the definition of the expectation. And what I have defined as L1, if you want to have it in mind intuitively, you can consider L1 as the set of the discrete random variable such that the expectation is well defined, in fact. That is, this sum gives rise to a number. It's not plus infinity, or even it is, in fact, convergent. Okay? So that's why I introduced L1. So I will write it this way. X discrete such that if I consider this sum, I want it to be finite. It's a condition I impose to be in this set L1. And I said that if I take a random variable that is in this space, okay, I know that this sum is finite, and so that this one is well defined. So expectation is okay in this situation. Okay? So it's just what I have said. Okay? So if it is too much complicated for you, forget it. Just keep in mind L1 as the set of the random variable for which you can compute the expectation. And in general, in practice, it will be the case. Okay? And we have seen together that in all the examples we have seen together, uniform, binomial, Bernoulli, Poisson, geometric, all of them belong to this one. And I was able to compute the expectation. We have seen for the uniform, okay, it's the mean. For the Bernoulli, it's P. For the binomial, it's NP. For the geometric, it's 1 over P. For the Poisson, it's lambda. We have done the computation together. Okay? So it's just what I have said during the previous session. Okay? That I want to deal this point of quantity and just define this space in order to be sure that this quantity is well defined. Point. Okay? And the thing we have proved that if I increase the power in the definition here, I have a restriction that is more and more restrictive, in fact. You have the set of all of them, the set of the one where the expectation is well defined, and we can continue. It's exactly what I have proved with this proposition. So today you are going to see that we are going to define the variance, and the situation will be this way. We'll have the set of all the random variables, the one for which you are able to compute the expectation, and the one for which you are able to compute the variance. Okay, less and less. You have more and more restriction to be able to compute the variance. Okay? So it was just to be clear concerning this point. Okay? So now I continue with the course. And you have this big proposition concerning the properties of the expectation. Here, let's say in the discrete case. And you will see that in other kind of cases, okay, it will be the same kind of proposition that we will have. Okay, so maybe let's have a look on what happened. So I won't do the proof in all details, okay? You have it in the list of proofs on my website, if you want to enter into details, okay, of the proofs. So I won't consider them, okay, as something to know for the exam, for example, the proofs, okay? I admit it in the course. So just say a few words concerning some of them because I read. Question? Ask me the question, please. Question? No? You don't want to ask me questions. The expectation has some interesting properties, and in general, so you can see this as some rules of computation for the expectation, and you will see that in general, when we compute an expectation, if we use this rule, it is often sufficient to compute concretely an expectation, and it's not mandatory to come back to the definition. Sometimes it's sufficient to use the properties. Okay? So just see, I will say a word on all of them, okay? I say that if x is bounded, necessarily my expectation is well defined. If I am a constant, my expectation is myself. Why? In 2 lines. So first, suppose that you have a random variable that is constant. Okay? I have a single value. Okay? So if I ask for the distribution of this one, okay, I know that the probability that x is equal to a is equal to 1. Okay? So if I apply the definition of the expectation, in this case I have a single value in my range. Okay? So I have to do a sum, but a sum with only one element Inside the range, I have small a, the unique possible value I can take. And the expectation in this situation is simply, by the definition, the only value I can take multiplied by the probability that take this value, single possibility, small a. Okay? So if I am constant, my expectation is myself. Okay? It's a very basic case in the computation. Suppose that capital X is bounded. What is the meaning of being bounded? It means that I can take a very large number of possible values, but each of them is less than a number. Okay? So I can write it this way. There exists M belonging to R plus, such that for all the value belonging to omega, the absolute value of xw is less than this one. It's what I mean by to be bounded. Okay? And if I am in this situation, I just want to show you that in this situation, I am in L1. That is, if I am interested in this sum here, L1 is with P equal to 1, okay? But this sum is in fact finite. Why this sum is finite? So keep in mind that the xi are the set of the possible values for capital X, meaning that all of them are less than capital M. Okay? Because my mapping is bounded. So why this sum is finite here?
That's less than the sum of, like, what, the sum of M?
So each one is less than M here. So I can say that this sum is less than M multiplied by the sum from I equal to capital I, the probability that X is equal to Xi. And what is this sum? I know it. 1. Okay. So you prove two things, in fact, that if you are bounded, you are in L1 because you have something that is finite here. And what is more, I have also proved that the expectation is less than M. So if I am bounded, I am in L1. So typically, if I take a finite number of possible values, I am in L1 because I am bounded if I take a finite number of possible values. Okay. X, there is a misprint in the slide here. Be careful. Okay. Second statement. Have a look. If X is L1, meaning that if I am able to define the expectation, I say that X positive implies something. But this something is not Y positive. What is Y? I don't have a Y in the statement here. So in this slide, replace Y by, in fact, the expectation of X is positive. Okay? So be careful. In the slide 12, of the part concerning discrete random variable, in the proposition term statement 2, here, it's not a Y that you have, it's a misprint, it's expectation of X. Okay? It is meaningless what I have written here. Okay? So why we have this, but once again, come back to the definition. Expectation is well defined if I am in L1. What happens if I take only positive values? But if I take positive values, here I have probabilities. So we have positive number. And here, it's the set of the possible values. I know that they are positive. So you have sum of positive terms. So you have something that is positive. Okay? So when the random variable is positive, its expectation, when it is well defined, is positive. Okay? L1 is a vector space and expectation is linear. What is the meaning of being a vector space? Nobody knows the definition of what is a vector space? for the double NEF, I know that you have a course of linear algebra. I will use few linear algebra in this course, okay, when we are going to work with random vectors, because I will need to deal with vectors, so with matrix, okay, and I will have some things to do, but very basic ones, okay. Just remind that a vector space E, or not E because E is for the expectation here, but F is a vector space if, I can write it this way, so one nice way to state is to say that any linear combination of the component is still a component. In other words, for all n belonging to n star, for all x1, xn belonging to f to the power n, for all lambda 1, lambda n belonging to r to the power n, the sum of the lambda I xi from I equal to 1 to n belongs to f. So it seems to be complicated, but I just say that if you take a finite number of elements in capital F, if you do a linear combination, it has to be in capital F. This is the definition of being a vector space. Okay? So what is the meaning of this in my statement 3? In my statement 3, it just means that if you have x1 that belongs to L1, if x2 belongs to L2, to L1, excuse me. So you have two elements in L1, let's say, and then lambda 1 x1 plus lambda 2 x2 also belongs to L1. So it means that if you are able to define the expectation of x1, if you are able to define the expectation of x2, then you are able to define the expectation of any linear combination of them. And the fact that the expectation is linear means that the expectation of lambda 1 x1 plus lambda 2 x2 is simply the expectation of the linear combination is equal to the linear combination of the expectation, is the meaning of being linear for a mapping. Okay. This is the meaning of statement 3. For the proof, list of proofs. It's not that complicated, okay, but we have to compute a little, and I don't want to spend time on this today. But keep in mind that expectation fulfills this rule. If you have an expectation of a linear combination, it's the linear combination of the expectations. Okay? So a priori, the set L1 is a vector space. It means that you can do the sum, you can multiply by a number, okay, and you are still in capital F. Be careful, I don't have said here that when you multiply random variable in L1, you have something that is in L1. In general, it's not the case. Okay, so I am a vector space. It means that I am stable by linear combination. It's the only thing I have said. If you want to do other operation, in general, it doesn't work. Okay? So, typically, if you have someone in L1, another one in L1, if you do the product, in general, you are not in L1. Okay? But you have a condition that allows you to have this. Okay? In fact, it's the statement 4. If I am in L2, so if X is in L2, if Y is in L2, then the product is in L1. So it means that I need to impose a little bit more on X and Y to have the product in L1. So keep in mind that you have L0, L1, L2. So L2 is a subset of L1. Okay? So imposing that X and Y are in L2 is something that is more restrictive than to be in L1. Okay? I am in L1, but I have a condition that is more restrictive. So why I have this one? So the meaning of this proposition, if I want to write it with words, okay, say that if you are able to define the expectation of x squared, if you are able to define the expectation of y squared, then the expectation of the product is well defined. And in fact, this result, that is true not only in the discrete case but for all random variables, is a consequence of a very basic inequality you know, that is this one. Why I have this? Oh no, if you want, but no. Something simpler and simpler than this one. What is this one?
Take the square of the sum of x and y, and you develop that square.
You won't obtain this one. It's not the sum that you have to take. You are not very far, but it's not the sum. Because, okay, whatever, yes, it's okay what I have written here. It's stupid what I have written here, in fact. Well, let's see what happened, okay? So what I have here, I have this square and I have this product here, okay? So, if I put this one here, I have a minus. So that's why I say to you that it's not the sum of the square of the sum that you have to consider, but I have this a minus b square. That is, of course, something that is positive because it is a square. You know that it is equal to a square plus b square minus 2 or ab. Okay? And so I have that ab is less than a square plus b square over 2. So it's not this inequality that I have to write. It's this one. Okay? This inequality just comes from the fact that this is a positive number because it is a square. Okay? And why my statement 4, or yes, 4 here, is proved this way? But if the expectation of the square is okay, that is, if the expectation of the square is a finite number, if the expectation of y square is a finite number, of course, the expectation of the product will be finite. So you have the proof that if the expectation of x square exists, if the expectation of y square exists, then the expectation of the product exists. In other words, it's exactly what I have written. If x is in L2, meaning that the square is in L1, if y is in L2, meaning that the square is in L1, then the product is in L1 through this inequality. Okay? So in general, if you multiply element in L1, you are not still in L1, but if you multiply element in L2, you are in L1. Okay? It's the meaning of this statement. Okay. Now, relation between independence and expectation. Relation between independence and expectation. We have seen together that two random variables are independent, okay? If I have the following, the probability that x belongs to A intersected y belongs to B, let's say, has to be equal to what? The product. Probability of the intersection is equal to the product of the probability, independence. So this is the independence between random variables, okay? In terms of expectation, what happened? I say the following. If the expectation of x is well defined, if the expectation of y is well defined, if the expectation of the product is well defined, and here it's a real hypothesis with respect to what I have said previously, because they are only in L1. So a priori, I don't know that the product is in L1. That's why I impose this condition. So it means that when I am able to write expectation of x, expectation of y, and expectation of xy, if they are independent, I have this formula. That is what? The expectation of the product is equal to the product of the expectations. That is just a generalization of what you obtain for the probabilities. Okay? So when I have independence, and when all the expectations are okay, then the expectation of the product is equal to the product of the expectations. Okay? Expectation of a linear combination is the linear combination of the expectation by the linearity. Okay? Expectation of the product is equal to the product of the expectation if the random variables are independent. Okay? And you have also the proof of this one in the list of proofs. Okay. So the two last things. So this one is really practical when you want to compute expectation in practice. Okay. And this one is I will use it maybe one time in the course. Okay, to define something. The last one is what we call the Jensen inequality. It is related to convex mapping. Okay. You know convex mapping because you start a course of optimization here, okay? And I have this formula. So, the proofs are in the list of proofs, but I want just to make a comment about this one. And for the statement 6, just let's take a basic example to understand what happened with this formula and what is this formula. Okay? So suppose that you have the following random variable, okay, that is x, that is from omega into, I will take this one, very basic case, this one, okay, 3 values. And I suppose that I have a uniform on this set. But what? Another 3. Okay. I am in this situation. Okay. So I am in definite case. Of course, it's possible for me to compute the expectation here. Okay. So what is the expectation of x? I use the formula, okay, it is what? Minus 1 times 1 over 3 plus 0 times 1 over 3 plus 1 times 1 over 3. I obtain 0 in this situation, okay? Just using the definition of the expectation. Now I said that I am interested in x squared. Okay? So x squared is also a random variable. Okay? What are the possible values for x squared? 0 and 1 in this situation. So I can find the distribution of x squared. What is it? But I have the probability that x squared is equal to 0. That is equal to what? What is the probability that x squared is equal to 0? But it's the probability that x is equal to 0. That is equal to 1 over 3. And what is the probability that x squared is equal to 1? 2 over 3, because it's the probability that x is equal to 1 plus the probability that x is equal to minus 1. Okay. So it means that x squared is also a discrete random variable. And if I want to compute its expectation, I just have to use the formula. It's the sum of the possible values multiplied by the probability to take this value. So the expectation of x squared, a priori, can be computed exactly in the same way as 0 times 1 over 3 plus 1 times 2 over 3. Okay? And here, what I have done exactly the same thing as I have done for x in order to compute the expectation of x squared. But what is the meaning of this formula? In fact, this formula means that what I have done here, in fact, it is not necessary to do this each time because I have a general formula in order to obtain the same thing. In fact. So here, the formula tells me that if I know the distribution of x, okay, I will be able to compute the expectation of j of x. Only knowing the distribution of x, meaning that it's not necessary for me to see what is the distribution of j of x, as I have done here. Here, in order to compute the expectation of x squared, I have computed the distribution of x squared. It's not necessary to do. I can pass directly from this one to this one through this formula here. Okay? This formula that tells me that the expectation of a function of x is what? Well, it's like the expectation. The only thing that is changing is that I change xi into j of xi. And in particular, if I take for j the identity function, I obtain that the expectation of x is equal to the sum of the xi multiplied by the probability that x is equal to xi. So I recover the definition. So if I use this formula in order to compute the expectation of my square in the preceding situation, okay? So what I have to do, I have to do the sum of the square of the possible values for capital X multiplied by the probability that x is equal to xi. So I obtain what? I obtain 0 square probability that x is equal to 0 plus minus 1 square probability that x is equal to minus 1 plus 1 square the probability that x is equal to 1. Of course, at the end, I obtain exactly what I have obtained here, that is 2 over 3. So I repeat that the meaning of this formula, and what you have to keep in mind is that when you know the distribution of x, in order to compute the expectation of a function of x, of j of x, it's not necessary to find the distribution of the new random variable that is j of x. It is sufficient to know the distribution of x and to apply this formula that is just a generalization of what I have done here. So the proof is in fact not more complicated than in these cases. I have just to introduce some notations that are a little bit boring to introduce, but it's exactly what I have done here. We do the computation and see at the end that we obtain exactly the same thing. So to compute, I don't know, the expectation of x squared, you are going to use this formula from now on. To compute the expectation of x cubed, you are going to compute, if I use this formula. To compute the expectation of exponential of x, you are going to use this formula, and so on. Okay? So in some textbook, okay, something that you can see in the name of transfer formula, but the formula to compute the expectation of a function of x, it's better to have it in mind this way. So a last word concerning the last statement here. Do you have questions? Okay? So the Jensen inequality. Of course, in my statement here, I have this convex. If you don't know what is a convex mapping, of course, it's not that clear what is this meaning. My question is, what is a convex mapping? What is a mapping that is convex? It's not that far for sure because we use the same name. Okay.
If you take any points in that set, all points between those points should be in that set.
So what you say is correct, and this is the definition of what is a convex set. So as you are going to see, So what you call all the points that are between, okay, are what we call, okay, barycenter, let's say, or linear combination that are convex combination. So just to illustrate what you have said here, a convex set, typically a convex set is this one. Something that is convex. What is the meaning of being convex? You take 2 points here, A and B. All the points between A and B are in my set. This is the definition of being convex for a set. It's not what I want here. I want the convexity definition for a mapping. But convex for a set means this one. Anytime I take 2 points inside, all the points that will be between A and B has to be inside. Typically, you don't have a convex set here, because if you take A here and B here, if you draw the line here, I have points that are not inside. So convex, not convex. So in fact, it's possible to use this geometrical aspect in order to define what is a convex function. So let's just I'll tell you an example. So I take this mapping, for example. Okay? So if I can be a little bit more correct, okay, I can draw it a little bit better in order to draw exactly a mapping that you know. What this mapping looks like here. Yeah, exponential of x. Exponential of 0 is 1, plus infinity, 0. So I have something like this here, minus infinity. And here I go to plus infinity. Okay? You see that in fact for the exponential, if I am interested in the upper part of the curve, that is this one, you have something that is convex. Okay, you take 2 points inside here, what you have between is inside. Okay, if you take the upper part of the course of the curve, you have something that is convex. So it can be one definition of the convexity using purely geometrical aspect. Okay, it's not the one I will give to you. I will give you the following one. J is convex if and only if the image of any linear combination is less than the linear combination of the images. What is the meaning of this? For all lambda belonging to 0, 1, for all x1, x2 belonging to R square, J of lambda x1 plus 1 minus lambda x2 is less than lambda J of x1 plus 1 minus lambda J of x2. So I repeat, I have my 2 points here, x1 and x2. Suppose that they are this way. If I take lambda in 0, 1, where I have to plot this point here? Where is this point here? My line. Lambda is in 0, 1. It's important to have lambda is 0, 1. It's what we call a convex combination here. A combination, a linear combination with the sum of the coefficients that is equal to 1, and all of them are positive. So where is the point lambda x1 plus 1 minus lambda x2? Yeah, well, it's between, okay? If you take lambda equal to 1/2, you obtain the middle. If you take lambda that is very small, you will be near this one. If you take lambda equal to something that is very near from 1, you will be near from x1. So you have a point here, just here. So the meaning of being convex for mapping means that the image of a convex combination is less than the convex combination of the images. From a geometry point of view, it means that I have the convexity of what I have drawn here. Okay? But I don't want to enter too much details. Okay, I just want to make you understand why we obtain this one. So if I have a discrete random variable with an expectation that is well defined, I consider a mapping that is supposed to be continuous and convex. If the expectation of j of x is well defined, okay, also, then the image of the expectation is less than the expectation of the image. The image of the expectation is less than the expectation of the image. So I have remind this definition just to show you that from an intuitive point of view, this inequality and this one are the same. Keep in mind to what happened in the case of a uniform distribution. In the case of the uniform distribution, you know that the expectation is just the mean or the weighted mean, okay? With coefficients that are probabilities, so that are all positive, with a sum equal to 1. So you have in fact, here, you have a convex combination in fact of the xi. You have a convex combination of the xi because the sum of all these coefficients here is 1 and they are positive. Okay? So an expectation may just be seen as an extension of linear combination or convex combination. And so, if I keep this definition, the image of a convex combination is less than the convex combination of the images. So, the image of the expectation is less than the expectation of the image. Okay? Because expectation may be seen as a kind of convex combination from this formula. Okay? So you have the proof in the lecture note. It's not that simple to prove the last one. You have to work a little. Okay? So, what is very important to keep in mind, it's not the last one, the first one. Okay? All these ones are very important in order to handle expectation. And what is nice, next week we are going to start the part concerning continuous random variable. In the case of continuous random variable, we will have exactly the same kind of properties. So you learn them one time, okay, and we'll learn them for all the cases in the course. And you will see that sometimes in order to compute expectation, but we are going to use this one. If I have independence, expectation of the product is the product of the expectation. If I have a linear combination, the expectation of the linear combination is the linear combination of the expectations, and so on. Okay? It will be some tools that will be able to apply. Okay. Do you have some questions concerning this proposition? So I just remind you that you can find the proof on my website in the document that is called Proof of the Course 1. Okay? And if I remind, this is the last proof of the document, list of the proof 1. After it will be list of proof of the course number 2. No questions? Is that clear? I continue. I have defined the expectation. Now we are just going to define the variance. The variance of a random variable. So once again, it's like what we have done in the case of the expectation. In the case of the expectation was defined as this sum. If I want it to be well defined, I need to impose x in L1. If you see the definition of expectation, let's see this one, for example. We are going to prove that both are equivalent here, but the variance will be defined as the expectation of the square minus the square of the expectation. Expectation of the square minus the square of the expectation. Okay, so it means that if I want to make this definition okay, I need that the expectation is well defined, and I need that the expectation of the square is also well defined. Expectation of x well defined means that x has to belong to L1. Expectation of the square well defined means that x has to belong to L2. Okay? Since L2 is included in L1, if I am sure that x is in L2, everything will be well defined. That's why I impose x to be in L2 to give sense to both terms here. Okay? So the variance is defined this way. Expectation of the square minus the expectation of x squared. So just to remark, if I have a look on this difference here, what can you say about the sign of this difference? Oh, do you see it on this expression here? And my question is, if you are able to see that you have something positive from this difference, not from this formula here, because in this formula you have the expectation of the square, so you have something that is positive. But for the moment, I just handle this expression here. Okay? Y expectation of x squared minus the expectation of x squared will give rise to something that is positive. I repeat, forget this. I don't want you to see this expression, just this one. Why this difference is positive?
Because we see that the expectation of gx will be
This one. You take j equal to x squared. J of x equal to x squared. You have something that is a nice convex mapping. Okay? And so, the image of the expectation is less than the expectation of the image. So, expectation of x squared is less than the expectation of x squared. And so, this difference is positive here. So, the fact that this difference is positive is a consequence of the Jensen inequality applied to the convex function x squared. Just to show you that sometimes this inequality may help you to say something. Okay? But in general, okay, to show the positivity, we come back to this analogous expression of the variance. So I start from this one. We are going to prove that this one and this one are equal. Okay? So if I take this okay, my aim is to prove that this one is equal to this one. Okay? What can I do? We have a square here. I develop. I don't have the choice. Okay, so I develop. If I develop my square, I obtain x squared minus 2x expectation of x plus expectation of x squared. You have three terms. Okay, you have the classical formula for the square. Okay, so x squared minus 2 times x times expectation and plus expectation of x squared. So I know now the properties of the expectations. I have all these properties here. In particular, that expectation is linear. Okay? So expectation being linear, I obtain this one. Expectation of x squared, so I will write it okay in two steps. So this time plus write it this way. I just use the linearity. Okay, the expectation of this sum here, the three terms, is just the expectation of x squared minus the expectation of this term plus the expectation of this term. What is this one here? Yes, because expectation of x squared is a constant. We have seen in the first statement that the expectation of a constant is the constant itself. So this one is expectation of x squared. This one. What can I say about this one? But I know that an expectation is linear. And here, 2 and expectation of x, it's a number. 2 times expectation of x. So I can remove it from the expectation, okay, by linearity. And so this term here is just 2 expectation of x times expectation of x. I repeat, because I remove from the expectation by linearity this term that is a number. And at the end, I have what? Expectation of x squared here, expectation of x squared, and minus 2 expectation of x squared. So I obtain this one. Okay? So I have proved here that in the definition of my variance, I give two expressions here. I just prove that they are equal. Okay? In order to make sense to this definition. And so in order to compute a variance, it will depend. Okay, sometimes it will be easier to use this one, sometimes this one, but in general it's more this one that we use, because in general, if you want to compute variance, first you have computed the expectation. So you already know this term here, and you just have to compute the expectation of the square. So I have this one. Other definition, what I will call later on the standard deviation, is just the square root of the variance. Okay? Standard deviation is just the square root of the variance. And I have the right to do this because the variance is positive number. So I can take its square root. Okay? And you will see that the standard deviation will be used a lot in statistics. Question? So you have the definition of the variance. Okay? We are going to see just after our propositions concerning the rules of computation of the variance. But first of all, okay, we are going to introduce the covariance. And why introduce the covariance after the variance? Because you see that you have links between both. So I will do a little remark that you are going to forget just after. But when you are going to do linear algebra, okay, you are going to see bilinear forms and quadratic forms in a few weeks in the course of linear algebra, or even in optimization or something like this, okay? Just keep in mind that, in fact, we are in the situation here where here you have something that is bilinear form, and here you have the quadratic form that is associated to the covariance. But you see what? In fact, you see that if you take, in my definition of the covariance here, y equal to x, you will recover the variance. If you take x equal to y, in the slide here, you obtain the variance. So I just erase this. I define the covariance this way. So it can be defined in two ways. This way, or the expectation of the product minus the product of the expectation. My remark is just that covariance between x and x is in fact equal to the variance, okay, from the definition I have written on the board. So you have here also, you have two expressions for the covariance, but to prove that they are equal, you do exactly what I have done in the case of the variance. You develop this one, you use the linearity, and you recover this expression. Okay? But what is interesting with this expression here is that you have the following consequence. When you have two random variables that are independent, the covariance is 0. Because I know from the previous proposition that if I have independence, the expectation of the product is equal to the product of the expectations. And so, if they are independent, the covariance is 0. Be careful, the converse is false in general. I don't have written here that if the covariance is 0, they are independent. It's not true. We are going to see together a counterexample for this in tutorial. And you will see a chapter in this course, that is the chapter dealing with what we call Gaussian vectors. And the advantage of what we call Gaussian vectors is that in this very, very particular situation, we have the nice property that covariance 0 implies independence. But it's not true in general. So for you, it's false for the moment. Okay? If you prove that the covariance is 0, you can't deduce anything about the independence of the random variable. If they are independent, the covariance is 0. If the covariance is 0, the covariance is 0. Okay? You don't have independence. So maybe before to do a little computation concerning the proposition 10, I just want to give you some intuition about the expectation and the variance. It's something that I have already speak about previously. I will erase here. We are going to do the last exercise of the list 3 in order to give you some intuition, I hope, concerning the expectation and the variance. The exercise 23 of the list 3 here. We are going to see that it is very basic. So exercise 23 of the list 3. Well, I have a discrete random variable. Here it is written finite, but whatever, okay, discrete. I want to prove this inequality here, and I want you to deduce the minimum of a mapping. So first of all, I am interested in proving an equality. That the expectation of x minus a squared is equal to the variance of x plus the expectation of x minus a squared. Why not? Okay? So, when I have to do this, okay, I can start from this one and try to recover this one, or start from this one and try to recover the other. In which side you do the job in general? So here I see that if I want to transform this one into this one, I have to complexify this one. If I want to transform this one into this one, I have to simplify this one. In general, what do you prefer to do? Simplify. In general, okay. But if you want, it's possible to pass from this one to this one. It's not that complicated, okay, but philosophically, in general, when we have an ugly expression, we want to make it better. Okay, not to transform something that is nice into something that is more complex. Okay. So let's start from this. Okay. What we can do, we can use the definition of the variance, and we can use to develop the square. Okay, so what is the variance? Expectation of x squared minus the expectation of x squared plus what? I develop the square here, that is expectation of x squared minus 2a expectation of x plus e squared. And you see that you have a simplification here. Okay, so here I use the definition of the variance. Here I develop my square. Okay, I simplify this term and this term. Okay, and if I simplify this term and this term, I remark that we have what? I remark that I have exactly what I want. Write it this way, it's the expectation of x squared minus 2ax plus a squared, that is equal to the expectation of x minus a squared. In fact, here implicitly here, I have used the linearity to obtain this one. Okay? So I have proved my equality here. You don't have to know a priori this equality, okay? It will just be helpful for the next steps. Are you okay? So it's just a computation, basic computation. I use the definition of the variance and I develop the square, I simplify and I obtain what I want, okay? So nothing complicated to say. Now, I asked for, so do you have some question? Ask me the question if you have. Yeah.
I'm a little confused as to how to, I'm forgetting, I'm blanking on the word, like, factor out an e out of the a squared. Because you have, every other term has, like, the expected value.
Yeah? A is a constant.
Is a constant? Oh, okay.
Yes, right. Here, what I have here, the expectation of a square is a square.
Okay, yeah.
So ask the question. Huh? Sometimes they are very short. Okay, I can answer quickly and. Okay. There are no stupid questions. Okay. So now I want to compute this, the minimum from A belonging to R of the expectation of x minus a squared. And I want the minimum, the point at which the minimum is reached. Okay, so if you want, you have a mapping that I can call, okay, f of A, and I want its minimum. Okay? So, of course, you do a cost of optimization for most of you. Okay, so you know, I have a very basic situation. Here I have a single variable. I can compute the derivative, see where it is equal to 0, compute the second derivative, see if it is strictly negative, and I will deduce that strictly positive in this case, that I will have a maximum or a minimum. Okay? It's of course not what we are going to do here because I have done a preliminary steps here. I have this one. So I want to minimize this. I know that this is equal to this one. So here you have a constant. So you don't mind about this one. If you want to minimize this one, you have to minimize this one. Okay? But what is this one? This one is a square. So when a square will be minimal, when this is equal to 0. When this expression is equal to 0, when A is equal to the expectation of x. Okay? I repeat. If I want to minimize this one, I have written this one as a constant plus this term. So minimize this one is equivalent to minimize the last one. Okay? For the last one, it's what? Expectation of x minus a squared. So I have to minimize something that always take positive value. If it's possible, if I prove that there is one point at which it is equal to 0, I will have my minimum. And I said it's all for small a equal to the expectation of x. So, minimum reached for a equal to the expectation of x. And what is the image of the minimum here? What is the minimal value in this situation? Variance. Okay. So first, are you okay with what I have said here? Okay, so I want to minimize this term. I repeat, it's equivalent to minimize this one. Here I have a positive number that can be minimized if it is equal to 0. And I see that if I take a equal to this one, I am 0. So I have the minimum for sure. Okay? Is that clear? So the minimum is reached at expectation, and the minimal value is the variance. So how to interpret this one? So I can't enter into all the details for the moment, but I can say that here you have a way, in some sense, to measure the distance between capital X and small a. Now you do the difference of the square or the difference of the absolute value, something that is not very far from a distance. So intuitively, if you want here, you try to quantify the distance between capital X and small a. Small a being a number, a constant. Okay? So if I want to minimize this term, okay, if I take my interpretation in terms of distance, if I want to minimize this term here, it's like minimize the distance between x and a number, and I want this distance to be minimal. In other words, I want the best approximation of capital X by a constant. The one that approximates the best capital X. The one with a distance that is minimal, let's say. Okay? The nearest, if you want. Okay? And I have proved here that two things, that this minimum is reached at the expectation. So intuitively, it means that if you want to summarize the information contained in a random variable by a number, you are going to use the expectation. If you don't have the choice, I just ask you, tell me what is this random variable with a number. But the number that is the most representative one will be the expectation. Okay? So it's what I have put here. And what is more, in order to quantify the quality of my approximation, that is, what is the minimum I obtain here, I see that the minimum is given by the variance. So if you have a variance that is very small, you will have, let's say, a good approximation. If you have a large variance, you will have a bad approximation. So I summarize. So approximate the best I can an expectation by a number is given by the expectation. To measure the quality of this approximation, I can quantify it by the variance, because the variance measures the distance between x and its expectation. Okay? When the variance is small, it means that the distance will be very small, and so my approximation will be good. If I have a big variance, I will have a bad approximation. Okay? Intuitive interpretation of the expectation of the variance. And in fact, it is not that intuitive, because I can prove, but it won't be the topic of my course here, that from this one you can define really a real distance in the space L2, okay, but whatever. Okay, so I just want to for you to have this in mind. You will see that when we are going to speak, okay, in a few weeks about conditional expectation, we are going to have analogous consideration. Okay, we are going to try to approximate a random variable by something that is no more a constant, but other things. And the best approximations will be what we call the conditional expectation. The expectation is the best approximation by a number. Conditional expectation will be the best approximation by someone that is not a constant. Okay? That is a little bit more complex than a constant. Okay, so it was just okay to give you some intuition about this. Do you have questions concerning this? F here. It's just the value, okay, of the function at its minimum. That is the variance. Okay? I just define capital F as this mapping. The one that I want to minimize, it is minimized at this point, and the value at the minimum is the variance. So I continue with my proposition here. The covariance is bilinear, in particular you have this. So what is the meaning of bilinear? Do you remind what is bilinear? So linear means that the image of a linear combination is the linear combination of the images, okay? Here you have the same, but for x or y. So if you make x move, y being fixed, you obtain something that is linear. And why it is linear? Because the expectation is linear. the expectation between being linear. If you make x moves and fix capital Y, you obtain something that is linear, and the converse hold. That is, if x is fixed and you make Y moves, since the expectation here and here are linear, the covariance will be, in fact, linear in each variable. That's what we mean by bilinear. Okay. So if you have a mapping here from, let's say, okay, I have this one. So I am interested in a linear combination, but only in the first component. I fix the second component. Okay, I obtain what? I use the definition. I obtain the expectation of lambda 1 x1 plus lambda 2 x2 y minus the expectation of lambda 1 x1 plus lambda 2 x2 expectation of y. And now I can develop, because here you have a linear combination. If I develop with the y here, I will have a linear combination at the end. Using the linearity of the expectation, I obtain lambda 1 expectation of x1 y plus lambda 2 expectation of x2 y minus lambda 1 expectation of x1 expectation of y minus lambda 2 expectation of x2 expectation of y. At the end, I recognize that I have, in fact, lambda 1 covariance between x1 and y plus lambda 2 covariance between x2 and y. So I have proved that I am linear in the first component if I fixed the other one. The same holds if I do the converse, that is, if I make moves y linearly and fix capital X, of course I will obtain the same thing, and in particular because, as you see in the formula, the covariance between x and y is the same thing as the covariance between y and x. If you change the order, it doesn't change the expression here. Covariance between x and y is the same thing as covariance between y and x from the expression here. Okay, so by bilinearity, it's exactly this one that I mean. I am linear in the first component and linear in the second component. Okay? The expectation is linear, the covariance is bilinear. And it implies that I have this kind of formula for the variance of a linear combination. For the expectation of a linear combination, it's the linear combination of the expectations by linearity. For the variance, I have this one. The variance of ax plus by is a square variance of x plus b square variance of y plus 2 times ab covariance between x and y. So I prove this in 2 lines. Okay, it's just computation, not complicated. Questions? So bilinearity means linear in each component. Okay? This one to compute, okay? And in fact, the way we are going to, so it should be possible, huh? It should be possible to plug ax plus by in the definition and to see what happens, okay? But it's not the way we are going to do, because I see that I have covariance that will appear here. So in fact, we are going to write the variance of the covariance between ax plus by and itself. Okay. So I write this one as covariance between ax plus by and itself. And now we are going to use the bilinearity. First, we are going to develop with respect to the first variable, and then we are going to develop with respect to the second one. So I obtain this one. I have, okay, so first we are going to do this. Okay? Okay? Using the linearity in each component. So it is equal to the covariance, I write it this way, ax plus covariance ax by. Okay, and then I do the other. This one. Plus covariance by ax plus covariance by dy. I use 2 times the linearity in each component. Now, once again, I can use the linearity in each component to show that the covariance of a times x, I can remove the a, remove the a here, remove the a here, because I am linear in each component. So I have a square covariance x, I have plus ab covariance xy, plus ba covariance yx, plus b square covariance yy, and so covariance between in and x is equal to the variance. Covariance between x and y is the covariance between y and x. So I have exactly what I want. That is a square variance of x plus b square variance of y plus 2 times ab covariance between x and y. Okay? In particular, if you have 2 random variables that are independent, it's a remark that I will do here, and after we are going to do the break. In particular, if x and y are independent, what can you say about this? You have the formula of the proposition 10 here. What can you say if you have independence? You can apply the formula for a equal to 1, b equal to 1. So you have the variance of x plus the variance of y plus 2 times the covariance between x and y. But if you are independent, what happens for the covariance? So the variance of the sum is equal to the sum of the variances. But be careful, it's not linearity of the variance, no? Because the variance is not linear. It's just because I have independence here. Okay, it's true because I have independence. So after the break, we are going to do the classical computation for the example we have seen together. We are going to finish with a more a remark than a new thing, okay, on discrete random variables, and then we are going to do the list 4 of exercise. Okay, I will do it today and I will finish it, okay, next Tuesday. So you are able to do now, okay, more or less all the exercise of the list 4. Okay? Okay, so do classical computations for the variance, okay, for the distribution seen together in class. So, what is this one? No, not the variance, because I want to compute it, but we have already computed the expectation together. Yeah? It's a computation I have already done. Okay? I want the variance. If I want the variance from the definition of the variance, it remains to compute the expectation of x squared. Okay? So is it clear what I do for everybody? Okay? You just arrived. Okay? So now I compute the variance for the classical distribution we have seen together. Okay? So you have the definition of the variance. I want to compute using this definition. And I said that when I have a look on the definition of the variance, I see that I have the expectation inside. So I will need to know what is the expectation first. And then it remains to compute the term that is expectation of x squared. So for the expectation of x squared, okay, we are going to use the formula in blue here, okay, for the square. What it will be the sum from I equal to 1 to n of I squared times the probability that x is equal to I. What is the probability that x is equal to I? 1 over n. I am a uniform on a set with n elements. Okay? Do you remind what is the sum of the square? The sum of the n first square. There is a formula that's the classical one for this one.
2 power n plus 1.
No. No. It's I that moves here, huh? Not the power that is moving. I. Okay? We have seen that the sum of the I is nn plus 1 over 2. And the sum of the I squared, do you remind? Or not, huh? It's not, if you don't remind, let me tell you. So it is 2n plus 1, n plus 1 over 6. But whatever, okay, so 2n plus 1 times n plus 1 over 6. If you don't know this formula, okay, it's a possibility, but you can prove it by induction. It would be a good exercise, okay, to do it by induction. So it's something to know, so only for this particular case, okay, for the exam it's not necessary to know it perfectly. If I want you to use it, okay, I will make you prove it, okay, excuse me, by induction, for example. And by induction it's very quick. Okay, but what is the expectation of x squared? So I continue my computation here. I have a simple simplification between n and n, okay, so I have 2n plus 1, n plus 1 over 6. It's not what I want to compute, huh? It's just the expectation of x squared here. So if I want the variance, I have to use the formula here. That is the expectation of x squared minus the expectation of x squared. Okay? So, variance of x is equal to the expectation of x squared minus the expectation of x squared. I use the definition. The expectation of x squared was just computed before, so it is 2n plus 1 over 6 minus the square of the expectation being n plus 1 over 2. Okay, so I obtain minus n plus 1 squared over 4. And the idea is to simplify a little. Okay? So first, if I want to simplify, I have to put them into the same denominator. So I multiply the first by 2 and divide by 2 and multiply the other one by 3 and divide by 3. And I obtain something like this, that is 2n plus 1 n plus 1 minus 3 times n plus 1 square over 12. So I see that I can put things into factor. I can put n plus 1 into factor here. Okay? So I do n plus 1 over 12 factor of what? 2 times 2n plus 1. So that is 4n plus 2 minus 3 times n plus 1. I just put into factor n plus 1 here. And finally I have what? 4n minus 3n and 2 minus 3. So I have n minus 1. So I obtain n plus 1, n minus 1 over 12. That is equal to what? I can simplify it a little again because I have, okay, an identity that you know, a plus b factor of a minus b. N square minus 1 over 2. Okay? N square minus 1 over 2 because you have a plus b factor of a minus b. 12. Okay? So I have this one for the variance of a uniform. Okay? I have this one for the variance of a uniform. You are lucky you can be sit, okay, I will prefer to be sit. We can change the place. Okay. For the Bernoulli of parameter P. Okay. What is the expectation in this case? So I have to compute the expectation of x squared, but here I am in a very, very basic situation where I have only two values, 0 or 1. So if I write the formula, it's 0 square probability that x is equal to 0, plus 1 square the probability that x is equal to 1. First term being 0, the other one being just equal to p. The expectation of x and the expectation of x squared are the same in this situation. So may I erase this? Are you okay for the uniform? Yeah? So you have the video, you have the slide, and you want to take picture? You will have a lot of materials to work. So I continue my computation here. And so the variance is what in this equation? It's the expectation of the square that is p minus the square of the expectation. So that is minus p squared. So I obtain p 1 minus p. Okay? And don't forget that p is a number between 0 and 1. That's why I obtain a number that is positive here. Okay? Variance has to be positive. If you do the computation of a variance and at the end you obtain a negative number, you have a problem. Okay? So we have this for the Bernoulli. The Bernoulli. For the binomial. For the binomial, in fact, it's possible to do the computation. If you remind the way I have computed the expectation, I start from a plus b to the power n. I write the sum with the c and k and so on. I compute the derivative in order to make the k appear. And I compute the expectation this way. In order to compute the variance, you can use exactly the same ID, but instead of computing the first derivative, you are going to compute also the second one. That will make appear a k square, in fact. Okay? So when you compute the derivative of a to the power k, you obtain k a to the power k minus 1. If you compute once again the derivative, it's k times k minus 1, a k minus 2. Okay? That make appear k squared. But it's not the way we are going to do. So I will prefer to use but a characterization of the binomial we have seen together. It's what we have used in the exercise, I don't remember, 22 or something like this, or 21 of the list 3. We have seen together that a binomial may be seen as a sum of independent Bernoulli. Okay? I can write x as x1 plus x2 plus xn. x1, xn are independent, and all of them follows the Bernoulli of parameter p. You can see a binomial of parameter np as the sum of n independent Bernoulli of parameter p. It's something that I have proved by induction 2 sessions ago. And now, what can I use if I am in this situation in order to compute very quickly? Well, the consequence of the proposition 10 we have seen just before the break, that if I have the variance of a sum of independent random variable, the variance of the sum is the sum of the variances. The variance of the sum by independence. So by independence, the variance of the sum is the sum of the variances. What is the variance of each one? So the variance of each one is p times 1 minus p. So the variance of each one is p times 1 minus p. The variance, not the expectation. The variance of each one is p times 1 minus p. So what is the variance of the sum? But it's n times the variance of each of them. So you obtain for the variance of a binomial n p 1 minus p. Okay? And here it's not necessary to do the computation directly. You can just use the fact that a binomial may be seen as the sum of n independent Bernoulli. Okay? So I have this one for the binomial, just using this trick that we have proved already together. Okay? The characterization of a binomial in terms of sum of independent Bernoulli. Poisson of parameter lambda. Okay? What was the expectation in this situation? Expectation of x was lambda. Once again, I have to compute the expectation of the square. So I use the formula of the expectation and or use what we have seen here, the formula in blue, this one. Okay, how to compute the expectation of a function of x. It's just so the possible values for Poisson are all the integers. Okay, so it's a sum from k equal to 0 to plus infinity, k squared. This case, the probability that x is equal to k, and by definition of a Poisson of parameter lambda, I obtain exponential minus lambda, lambda to the power k, over k factorial. Okay. And I can remark that in fact my sum doesn't start at 0, in fact, concretely, but start at 1 because the term for k equal to 0 is 0. Okay? If you plug 0 here, then you obtain 0 because you have k squared here. So my sum starts in fact from 1. What can I use to do this? In fact, for the moment, it's the same idea as the one we have used in the case of the computation of the expectation. What can I do here? So, for k greater than 1, I have that k over k factorial, or greater or equal to 1, is equal to 1 over k minus 1 factorial. I can simplify. Okay, it's exactly the idea I have used in the case of the computation of the expectation. So we are going to use this, and it will allow us, okay, to pass from k squared to k. So I continue my computation here. I have the sum from k equal to 1 to plus infinity, k exponential minus lambda, lambda to the power k over k minus 1 factorial. I simplify just by k in this expression to obtain k over k minus 1 factorial. Okay? How to continue here? Now it's not possible to simplify. Huh? An idea how to continue? Yeah? It's a good idea because, in fact, if I have instead of k minus 1 factorial k here, I am able to do the computation because it's just the expectation. Okay, but here it's not what I have. But if I change the index, I will make appear a 1 over k factorial. That is what I have in the definition of the probability mass function of my Poisson. Okay? So if I change my index here, I define a new index to be k minus 1. Okay? This one will be the new index, meaning that if I start from 1 to plus infinity, but if I transform my index from k into k minus 1, I will be from 0 to plus infinity. So, if k becomes k minus 1, k will become k plus 1. Okay? I have this one. And I said that in fact this one is simpler to handle. Why it's simpler? First, because I can make appear here the probability mass function of the exponential of the Poisson of parameter lambda, because lambda to the power k plus 1 is just lambda to the power k times lambda. So I can put a lambda before and write this. Have this. Now, what can I do? But I know that if I have this one, I am able to compute because it's the expectation. If I have this one, I am able to compute. It is equal to what? The sum 1. Okay. So I split in 2 parts. Okay. If I split this sum in 2 parts, I have the sum from k equal to 0 to plus infinity k exponential minus lambda lambda to the power k over k factorial plus the sum from k equal to 0 to plus infinity exponential minus lambda lambda to the power k over k factorial, and I am able to compute each of them. The first sum has been already computed because it's just the expectation of my Poisson. The second one is just equal to 1 because it's the sum of the probability mass. It's the sum over the possible value of the probability mass function. So I have lambda factor of lambda plus 1. And now, what is the variance? Well, the result I have obtained, that is the expectation of x squared minus the square of the expectation of x, the square of the expectation, that is lambda square, and so I obtain, in fact, the same thing as the expectation. The variance of a Poisson of parameter lambda is also lambda. Okay? Expectation is lambda, variance is lambda in the case of a Poisson of parameter lambda. So something very easy to have in mind, the same thing, lambda, the parameter. Okay? So the idea here is to try to simplify the beginning as we have done in the case of the expectation. And when I am at stage here, the idea is to change the index in order to come back to sums I know. Okay? In order to come back to sums I know. So it remains the last case to do. And I leave you this one for you at home to do. Okay, so I want to do the computation in this case. Do you know the result? The variance of a geometric of parameter p? It's no, huh? If you don't know, you don't know. Yeah. Nobody? Remind? So if I remind, I am not sure about the results, but I am able to compute it quickly, but I remind something like this. 1 minus p over p squared. So the expectation is 1 over p, and the variance is 1 minus p over p squared. So I want you to do at home, and I just remind you the idea about this. Keep in mind that in order to compute expectation in this case, we have started from this kind of sum, okay, and we know that it is equal to this one if x is not 1. In order to compute the expectation, I have computed the derivative of this term. In order to compute the variance, you are going to compute the second derivative and see what happens. Okay? So compute the second derivative of in this equality here. You will have a big expression. Then make n goes to plus infinity, and you will obtain, okay, what you want. So try to do at home by yourself this one. It's just a computation of a derivative that you have to do 2 times. And then, okay, so have a look on what you have done in the case of the expectation. It's exactly the same thing, computing the second derivative instead of the first. Okay? So at home. And you have the result. Okay. So we have the values in our classical cases: uniform, Bernoulli, binomial, Poisson, géométrique. Allez, to conclude the course concerning the discrete random variables, It's more a remark or a little definition, okay? And it will be the first step towards something that we are going to do more systematically after. That is, okay, for the moment we have handled single random variables, one random variable. It's possible to handle several at the same time. It's what we call random vectors, okay? It's just a vector for which each component is a random variable, okay? So are you okay with the computation of the Poisson? Yeah? Arrays? And I conclude my course concerning discrete random variable with this little remark here. That will be extended, okay, in few sessions. And then we are going to do exercise. And I will also start with exercises next session. Okay, so in the list 4 of exercises, you have at the beginning of the list 4 the exercise we are going to correct together. Now you are able to do everything, all the exercise, because we have finished almost the course concerning discrete random variables. And I think that it's better to try to, so the first one has already, we have already done this one together, so it remains this ones, okay? I will start today, but for the one that I won't have the time to do today, try to do them at home by yourself. It will be more efficient when I will do the correction in class, okay? But before to do this, come back to my remarks. So instead, I repeat, instead of working with one discrete, we are going to work with two discrete. And of course, the same will be okay for 3, 4, 5, a finite number. Okay? So I consider x from omega into r. I suppose it to be discrete, meaning that it takes a number of possible values that is at most countable. Okay, so and I will give the name of the possible values. So the range of x is just for me here, xi, I belonging to capital I being countable. It's exactly what I have done from the beginning. I consider another one, y. Y that will also be discrete, but with a set of possible values that may be different. The only thing that I know is that since I am discrete, it means that the set of the possible values is at most countable. Okay? Maybe finite or countable. So I have y from omega into r. I denote the set of the possible values yj for j belonging to capital J being countable also. Okay? So it may be finite or something that, if you prefer, is a sequence. Yes. So I have two discrete random variables. I can try to see what happens for the pair. I can define the pair this way. So the pair will also be a mapping from omega. But what are the possible values? But I won't be in R, I won't be in R square a priori. And it associates to W just the number XW, YW. Okay? It's what I call by a pair of random variables. It's just this mapping. What is the set of the possible values here? What is the range of this one? My possible values for capital X are the xi. My possible values for the capital Y is yj. What are the possible values for the pair xy? So I can write it this way. For ij belonging to I times j. Okay? Another way to write this is just to say that it is the range of x times the range of y. Simply. The first component is an element in the range of x. The second component is an element in the range of y. So I have a new random variable starting from my two discrete one. What can I say about this one? If capital X and capital Y are discrete, what can I say about this? It is also discrete because, okay, when you do the product of countable sets, you obtain something that is countable. So here, I times j being countable, then the pair xy is a discrete random variable. That just take values in R square. Okay, why not? Okay. So the definition I introduced here is the extension of the notion of probability mass function in the case of a pair. But it should be the same for a triple, for a quadruple, and so on, for any n-tuple of random variable. So in the case of 2, what I call, well, I have the definition on the slide, so it's not necessary to write it. So I am in my situation I have explained here. I consider my two discrete random variable. Okay, and what we call the joint distribution of x and y is just the distribution of the pair, and we know that the distribution of a discrete random variable is characterized by the probability mass function. And what is the probability mass function here? It's the probability that the pair xy is equal to the pair small x, small y. But what is the meaning of this one? A pair is equal to another one if they have the same component, in fact. Okay? So it means that it's the probability that x is equal to small x intersected with y equal to small y. To say that a pair is equal to another one means just that the first components are equal and the second component are equal. And this number is what I call the joint distribution of the pair xy. And I give it a name that is just P of x, y, xy. That is this one. It's the aim of the definition 14. And in fact, I repeat, it's just the probability mass function of the pair considered as a discrete random variable. Okay, little remark in blue here, the last line of the slides. Here, I have, of course, no hypothesis concerning the independence or not of capital X and capital Y. Okay? I don't know. In general, they won't be. But if they are, what will happen? If they are, I know that if X and Y are independent, the probability that X is equal to X intersected with the probability that Y is equal to Y is equal to the product of the probability. And in fact, it's the definition of independence in the discrete case, okay? So I can say the following. In order to prove that two random variables that are discrete are independent, it is sufficient to prove that, so I will use the words of the definition, that the joint distribution, okay, is equal to the product of the distribution of each component. Okay, so just meaning that the probability of the intersection here will just be the product of the probabilities. So if I give you a joint distribution, you will be able to check if you have independence or not, if you are able to write the joint distribution as the product of the distribution of each component. So it's my first remark, okay? You have a link between the joint distribution and the notion of independence. Two random variables will be independent if and only if the joint distribution is just equal to the product of the probability mass function of each component. Okay? And in general, okay, if I want you to deal with a pair of random variables, from the statement you will have these quantities. I will give you the probability mass function of the pair. It should be possible to see if they are independent or not. Okay. And I will conclude by this little remark here. So if I give you these numbers, okay, I give you these numbers from a statement. I have a pair xy and I give you all these probabilities here. My objective is the following. So suppose that they are known, given by a statement. That is, I give you the joint distribution of a pair. Okay? My question is that I want to have this. I want to obtain this one from the number you know that are the previous one. All this one. Or to obtain this one from all this one here. Or to obtain this probability, that will be the probability mass function of capital X from the knowledge of all these probabilities here. So the idea is, you can see this as the law of total probability, or also just a consequence of the sigma additivity. So what can I say? I can say that if I consider these events here, y equal to yj, for j belonging to capital J. What can I say about these sets? I can say that I have a partition of the universe, in fact, because it's the set of all the possible values. The yj are the set of all the possible values for capital Y. So you have here a countable partition of the universe, meaning that they are pairwise division because it's not possible to take the same value and two different values at the same time, okay? And the union of all of them is equal to omega because the yj are exactly the set of all the possible values for capital Y. Okay? Now when I have a partition of my universe, okay, I can use the law of total probability. Okay? The law of total probability that tell me that the probability is this one that I want? Yeah, I can write it this way. The probability that x is equal to small x will be written as a sum, okay? That may be infinite or not here, but whatever. The sum of what? Probability that x is equal to small x given that y is equal to yj, probability that y is equal to yj. Okay? It's the law of total probability applied to this partition of my universe. Okay? So I have this one. And what I have to keep in mind now, let's just keep in mind that by definition of the conditional probability, the conditional probability is the probability of the intersection over the probability of the second set here. This is just equal to the probability that x is equal to small x intersected with y is equal to yj. And so, as she said, if I do, so I consider, and I know these terms, I consider the joint distribution function. If you do the sum the partial sum with respect to the values of the second random variable, you recover the probability mass function of the first. And if you do the converse, it's exactly the same proof. P of y, that is the probability mass function of y, will be recovered doing the sum over the sum of the joint distribution over the set of all the possible values for capital X. Okay? So if I give you this one, just being able to computing sum, you will be able to find the probability mass function of X and the probability mass function of Y. Okay? So you will have this one, this one, this one, and to check if they are independent or not, you can use this one. If the product of these two is equal to this one, you are sure that they are independent. If it is not, they are not independent. Okay? So it closes what I have to say for discrete random variables. Okay? So we stop with the course now. We are going to do exercises. And next week, okay, so I will finish the exercises concerning discrete random variable, and I will start a chapter concerning continuous random variables. And you will see that we won't have too much difference between these two chapters, instead of the fact that in this chapter we have computed sums, in the other chapter we are going to compute integrals. Okay? So I stop with the course. We are going to pass to the list 4 of exercises. You have this one on the board there. And I want you to do, and I will let you time in order to work a little. I want you to do the exercise 3. That is the following statement. You have two independent Poisson distribution. I want you to prove that the sum is a Poisson with a parameter that is the sum of the parameters. So exercise 3, and if you have already done this one, okay, you can do all the other ones, okay, from the list. May I erase the blackboard, or do you have some questions? Okay? So I erase. We are going to do the exercise 3 of the list 4. You are going to do, try to do by yourself, okay? Correction of the exercise 3 of the list 4. So we decompose x plus y equal to k into simpler events depending on the value of x. Another way to do will be also to use the law of total probability. It is possible and you obtain exactly the same thing. Okay, so keep in mind that at this stage, the only thing I have used is the fact that I take values in n. I don't have used the independence and I don't have used the fact that they are Poisson. So what we are going to use now? I have the probability of an intersection. Independence. Just have a look because I have moved my computer. Yes. Sum from I equal to 0 to k of the probability that x is equal to I multiplied by the probability that y is equal to k minus I, and to write this equality I use the independence in the statement. Okay, so it's here that I use the independence. Now to have the probability mass function of x and y, we are going to use the hypothesis concerning the distribution of x and the distribution of y. So I continue my computation here, and the probability that x plus y is equal to k can be written as, so the probability that x is equal to I is equal to what? So x follows the Poisson of parameter lambda 1. So I have exponential minus lambda 1 to the power I over I factorial. Okay? That is the probability that x is equal to I. X following a Poisson of parameter lambda 1. For the other, the probability that y is equal to k minus I. Y follows a Poisson of parameter lambda 2. I have lambda 2 to the power k minus I over k minus I factorial. What to do now? So you have the answer you have to find. Huh? We give you the answer in the statement. That is what you want to find is that the probability that x plus y is equal to k is equal to exponential minus lambda 1 plus lambda 2, lambda 1 plus lambda 2 to the power k over k factorial. Okay, because I want to prove that I have the Poisson of parameter lambda 1 plus lambda 2. My question is how to recover what I want from what I have here. First, I have already the exponential. Okay, already I have the exponential. It's not that bad. I have the exponential, so the beginning of what I want. Okay, and I have a sum. Okay? And in fact, it's important to know the answer, huh? But you know what you need to have. Okay, so an idea, something that you want to do?
It's in the numerator, it is a part of that. Yes?
It's a part of?
The combination.
Yeah, exactly. So you can see this way, or you can also say something that is completely equivalent, that is, I want this. In this expression, I have k factorial, 1 over k factorial. I don't have it here. I make it appear. I want it because I know that I will need it at the end. Okay? But it's exactly what you say, in fact. Huh? Exactly. You see that here, in fact, I have the beginning of the combination notation. Okay? Another way to say is that I want the 1 over k factorial. I write it, but if I do this, I have to multiply by k factorial. I have to multiply by k factorial, and I can make it enter into the sum because it doesn't depend on the index. So I have k factorial here. Okay? And in fact, I remark that I have something that I know from the prerequisite here. What is this one? This one is C K I. If I remember, so just a remark with this. I have received 1 or 2 emails concerning the notation and say, okay, why do you take this notation? I know other notations, okay, it's complicated for me. I am totally agree. The problem is that you are coming from all over the world. And if I take, let's say, 5 different books of 5 different countries, you will have 5 different notations. Okay? So that's why I have decided at the beginning to take something that will be my notations, okay? To be clear for everybody. Imagine that when I correct an exam, it's not possible for me to pass from, okay, a notation from the United States, from notation to Vietnam, China, okay, Europe, okay? So I will use this one. I know that there exist other, typically, okay, in the American style. but it's mine. Okay? And it's the one I want you to use. Okay? And that's why at the beginning of the prerequisite I have tried to, for the name of the sets and so on, to be clear together. Okay? So I have this. You agree? It's finished, in fact. You finish up to something you have to know, because it's something we have already seen together. So the sum that interested me here is this one. And what is this sum? So you know what you need to obtain, okay? So you can say, okay, it's this one, but I'm agreed that. But the argument is just remind that we have seen together and proved together that a plus b to the power n in Written as the sum. So I will use the same notation: I from 0 to n, c n I, a to the power I, b to the power n minus I. So you have here exactly lambda 1 plus lambda 2 to the power k, and you obtain at the end exactly what you want. So what is interesting is this exercise is just to say, so you have the beginning of the exercise that is interesting because it may be adapted to other kind of situations, not necessarily the Poisson one. I start to use my statement here with the independence. So what I have written here is true in the case of any type of discrete independent random variables, and it's here that if I want to continue the computation that I need hypothesis on the distribution of x and the distribution of y. I do, and at the end I have this one. And I know the result. So since I know what I want to obtain, I have a good indication on what I have to do, in fact. Okay? It's not the same exercise if I tell you find the distribution of x plus y. It's a little bit more complex because you don't know what you have to find. Okay? Yeah, I give you the answer. That's why to make appear the k factorial and so to make appear the c key I, okay, it's not that surprising. Okay? So I will finish by this today because, as you know, I have a priori to finish 10 minutes before. So in the morning I don't do this because we are the first in the room. On Thursday, you don't have class before, the room is free, and after it's me that I have the room half an hour later. So in fact, it's the only time where I take these 10 minutes, okay, for the order that will come in the room. Okay? But we start at 9, we start at 1 on Thursday, okay, but we finish 10 minutes before this day. Okay? So see you next week.